be of service. Okay, it is 5 minutes after the hour, so why don't we go ahead and get started? I am Don House, the Director of Teacher Programming at the Paleontological Research Institution. Geez, must be tired if I'm getting the name of my own place wrong. We are hosting today Ben Brown-Steiner, who's going to talk about climate modeling. Ben is a PRI research associate and working mostly at the National Science Foundation today, but doing this workshop as part of his role as a PRI research associate. And we do these workshops after a free online workshop after the publication of each issue of the Learning Earth newsletter, which comes out 5 times a year. We line it up roughly with the 4 marking periods in New York State schools and have a summer issue, which will be out in June in a couple of weeks. And you can see the link to the current issue that announced this workshop, as well as a subscription link in the chat. And I will also note that it announces, the current issue announces our summer workshop, which will be face-to-face in Ithaca, New York at the Museum of the Earth in August. And with that, I'm going to hand it off to Ben Brown-Steiner. Take it away, Ben.
Great. Thank you, Don. Nice. Thanks for having me. I like this topic, so I'm happy to talk about it. And I'm excited about the interactive part towards the end here. That should be a lot of fun. And just as a quick background of my experience, I trained as an environmental engineer as an undergraduate. I got my PhD at Cornell, which is how I met all these nice people at PRI, in atmospheric chemistry and climate science. I then moved to Boston, where I currently am. I did a 2-year postdoc at MIT, then worked for 4 years at a private company on atmospheric modeling, kind of broadly defined. And now I'm at the National Science Foundation as a rotator. And for those that don't know, National Science Foundation is one of the biggest basic science funding institutes in the US. And they have this program where they bring in experts in the sciences and engineering and all the fields for 1 to 4 years. They help manage the review process and recommend projects for funding. And I'm in my 3rd of 3 years of my rotation. But this is my role as the research associate with the collaborators at PRI. And let's see, let me share my screen. That's right, let me get on that. Share my whole desktop over there. And it'll be a little weird because my screen's over here and you're all here. So you're gonna see the side of my face a lot while I'm talking, but that's fine. And just there's kind of 3 parts to this presentation. The first one, just because I'm not sure everyone's background history, what is a climate model? So just a little kind of grounding of what a model actually is. There is a dip into some philosophy of science, because when we're talking about ensembles, which is what the most of this talk is about, you deal with uncertainty and chaos, and to really grasp what's happening there, you do have to understand a little bit about how science does what it does and what that all means. So there's a dip into philosophy of science. And then at the end, the third part is looking more closely at climate model ensembles. We'll be generating our own ensemble in kind of a toy model sense. And then I'll show you some nice websites where we could explore to look at actual ensemble output for different regions of the world, and in the US for very particular locations in the US, which is very useful. I do have 3 points where I'll pause for questions, for general questions. But if there's a clarifying question or something that is a quick question, you can interrupt or raise your hand or drop it in the chat, which I'll try to monitor. This is meant to be more interactive. I'll talk a bunch at the beginning, and then towards the end, it'll break down into more of a back and forth interaction. So to kind of start, some of you might have these mugs or have seen these mugs. They're kind of silly. It's a mug that, when cold, on the right shows just the sea level that we know today. And if you add hot water to it, it transforms on the left into a representation of sea level rise at some point in the future. And I like this example because under any definition that I can kind of come up with, this mug is a climate model. It does everything a climate model does. It has model structure, it has initial conditions, it has input. You can tweak it. It has a time evolution. It's not a good model. in a lot of ways. There's no citations. There's no way to play with the parameters. There's no way to figure out what time of the future they're looking. It's a really bad model, but at its core, it is a climate model in all of its definitions. So as moving on from the MUG model, I'm just going to talk real quick about kind of how these climate models developed over time conceptually to where they are today. And way back in the beginning, before computers were around, and all of even before scientists were called scientists, they were natural philosophers, they had a conception of the Earth in space in relation to the sun. And when they were doing all of this in their mind and on paper, they had to go simple with it. They couldn't do gridded models. So initially, a good way to think about it to start is the whole atmosphere, all of Earth, is a single system, a single homogeneous system. There's no layers. There's no difference in latitude, longitude yet. And they were trying to figure out, well, what is the temperature of the Earth? How can we figure out the temperature of the Earth based on the sun? And when I was doing my training as a climate scientist, we had some of these models. We looked at some of these. And the assumptions for these are radiation comes in from the sun, some bounces off the Earth or the clouds, some is absorbed by the Earth, and then some is retransmitted. The Earth warms up and retransmits out to space. A very simple, zero-dimensional representation of the climate system. And if you make some assumptions and do some measurements, you can kind of very quickly get an estimate of what the surface of the Earth, should be. And in this particular example, you run the math, you run the equations, you get negative 21 degrees Celsius, which is certainly not accurate for this surface of the Earth's temperature. But interestingly, if you kind of look at the average surface temperature of the moon, which isn't really all that great because there's no atmosphere, it ranges in the nighttime from negative 183 degrees Celsius up to 106 degrees Celsius during the day. So if you squint and average those, you can kind of get a minus 21 degrees Celsius. So it's a good representation of just what a rock in space, would be that was roughly the location of the Earth. So great, like zero box model, you can do it pretty quick and you can get a pretty easy idea of what's happening. Of course, we know it's way more complicated than that. And one of the major things that we have to pay attention to is the differential heating, that the way that solar radiation passes through the greenhouse layer is absorbed by the Earth, which retransmits heat back up, that is absorbed by that greenhouse layer. And that's essentially the greenhouse effect and really changes the whole system. So instead of just a single point, if we do a 2-layer model, assuming everything else is homogeneous, but we just have 2 layers in the atmosphere, you can come up with a slightly more complicated representation. I'm not going to run through all of the details here. Any basic climate book will kind of walk through this, but you do this calculation, and instead of just one temperature, you have a surface temperature and an atmospheric temperature of that layer. And in this case, running through the math, you get the surface temperature of about 11 degrees Celsius, which is pretty accurate for surface temperature globally on the Earth. And then atmospheric layer temperature, you get negative 35 degrees Celsius, which again is relatively accurate for the upper atmosphere. And so already we can see that this is it's getting complicated even at this scale, at this 2-layer scale. You can add more layers if you want. This is a 3-layer or a surface and 2-layer example, and you can run all the math. But ultimately, if you add all the layers, you get the atmosphere that we know, which looks like this. And just briefly here to understand what this is, there are multiple layers in the atmosphere. We all live in the bottom. Can you see my mouse on the screen? Okay, great. The bottom layer of the troposphere is where we all live and where all the weather that we know exists in. And we know here if you climb mountains, it gets colder as you go up. So in the troposphere, the bottom layer here, as you increase in altitude, the temperature decreases. At some point at about 10 kilometers, that switches and it inverts, which is the top of the tropopause. This is in part because of the ozone and greenhouse effect kind of here in the stratosphere, which warms up to the top of the stratosphere. And then it gets wonky when you go up more into space because the atmosphere is so thin, even the concept of temperature breaks down somewhat. That's why you have this crazy spike in temperature in the very upper, because molecules don't really run into each other very often. So their speeds are crazy fast and temperature doesn't really mean something up there. But this would be let's say 100-layer representation of the atmosphere. You can get this pretty regularly. We also know that, of course, just doing layers doesn't make sense. There's way more going on the Earth than just layers. So one thing you can do is say, well, we'll split the layers up into zones, north and south. And one of the models that I ran at MIT did this. It was a zonal climate model that had slabs going across, east-west, but didn't have any differentiation of east-west, didn't break it up that way. And the strength of these models, even the ones that are used today, is that they're simple to run, they're not computationally expensive, and so you can run hundreds or thousands of simulations exploring all the parameter space. You get a really, really good feel for the spread of various climate parameters with this model. But then again, you can't tell the difference between North America and Europe and Asia because they're all averaged together in one zonal slab. So the models that we all use primarily today are these three-dimensional climate models that break up the entire atmosphere and air system into grid boxes that are north, south, east, west, and height dimensions. And that is largely what we talk about when we talk about climate models in these days. To complicate things a little further, in all of these grid boxes, you don't just have an atmosphere. You have an atmosphere, and you have ocean, and you have life, and you have ice. So you have to think about, let's say you have one grid cell over the ocean. You have to think about the interactions between the atmosphere and the ocean, the fluxes of moisture and heat and temperature and all that. If you have land as well, you got to figure out the cycling and the fluxes between all those pieces. And then you can even get down to further detail to subdivide these. And very quickly, you get this kind of generic look of, we've split everything up in tiny little grid boxes, and you have to track the flows, and it gets computationally expensive very quickly when you try to get down to low resolutions. And this is the details of this aren't really important, but there's a lot going on in the models that needs to be established and figured out before you even push run the first time. When I started doing my climate work, this was kind of the state-of-the-art resolution of climate models, which was decent at the time. Nowadays, we have much better computational capabilities, and so we're able to get a much finer look at what's happening. One thing to note in this is that this kind of north-south grid that was very much the baseline for a long time has issues at the poles where all of these lines converge. You get distortion in the area of the grid box. So the grid boxes at the equator are kind of nice and square and simple. When you get to the poles, you can get some wonky things happening. So you have to play with that. Nowadays, there's a pretty exciting moment where all of these different grid representations are kind of coming into play, in part to get rid of that polar distortion. So there's some here on the right. There's this hexagonal grid that doesn't have any all of the globe is the same grid, hexagonal grid. You just then have to pay attention to how you're having fluxes in and out because it got more complicated. The middle one is an example of a triangular grid that works pretty well. The red zone here is a nested resolution where some of these models you can zoom in and pick particular regions and increase the resolution, but leave the rest of the globe at a coarse resolution, which lets you save some computational time. And then the one on the left is used quite a lot these days. It's called a cubed sphere. So essentially, if you took a gridded cube and just puffed it up to a sphere, it would look something like this. So you don't have the distortions at the poles, but you get some weird things at the corners of this cube sphere, so there's trade-offs with that. And then another really interesting and exciting thing is the ability to do pretty complicated nesting of grids, where let's say you really care about the climate over New York State, but you don't want to run the entire globe at that higher resolution. You can do these multiple nests or these nests within nests to get all the way down. And these work well, but sometimes you get weird things happening at the edges of the nested resolution. So there's things to track there, but that is like a real quick just run through of what, of where climate models are now. And I will open it up to questions at this point, because I know that was like a rapid fire walkthrough. Are there any questions or comments at this point?
You can either turn on your camera and raise your own real life hand, or you can click on the reactions button at the bottom of the Zoom screen to raise your virtual hand if you have questions.
And I do see one. Yes, David.
I was just wondering, are you going to talk, if you're going to talk about this later, you can defer later, but what is a typical runtime for some of these fairly dense nested cubes that you've been talking about?
Yeah, it depends on the infrastructure that you have. Most of these complicated ones need to run on supercomputer structures, and depending on the size, it can be quite quick. When I was doing the modeling run, I would get usually a month of simulated runtime every hour or so. And so if I was doing, a 30-year simulation, it would still take days on a supercomputer to kind of chunk through. With the ability to do parallel computing and stuff in the cloud, you can really, if you have enough money to kind of rent enough cores, you can do this rapid fire. But that costs money. Some of the models, the simpler ones, you can still run on your computer or your phone sometimes. Some of those basic ones, so those are much simpler, of course, but those run almost instantly. I have an example later on that I can show of a climate model that's essentially a Excel spreadsheet, that kind of runs instantly when you change the parameters. Yeah.
James, you have a question?
Yeah. So here in Australia, we have the Bureau of Meteorology and CSIRO, which do climate models. And I assume in the US it's like NOAA. How many different because how many different organizations actually, what am I trying to say? The climate models that are run, big organizations run them. And roughly how many are there in the world which are actually running these climate models?
That's a great
tens
question.
or hundreds?
Yeah, I would say it's between 10 and 100 that are often used, which is not a great answer. But yeah, at the end, we'll be able to look at, there's a website that summarizes in a model intercomparison sense all of these models. And in that comparison, there's usually 20 or 30, that have run all the simulations and can compare what's happening. There are many more out there, but not all of them participate in those intercomparison projects. But I would say, the major ones probably on the order of 30 or 40, and then there's maybe double or triple that are out there that do specific things. Yeah. William.
Yes, I was wondering, on our local weather station out of Penn State, they talk about the European model or the US model. What is the difference between those two?
Yeah, I mean the entire history of the model development is the difference between those two, and part of that is just different scientists worked on them and coded them initially, back when they started doing coding of these models in Fortran 40 or 50 years ago, and a lot of the components in those different European versus US models are the same science, the same parameters, the same equations, but they were put in different, or the structure of the model was somewhat different.
Okay.
Yeah, and there's great value in having models of very different histories, because I'll talk about that a little bit at the end. The intermodel comparisons are a very powerful way to explore some of these uncertainties.
Thank you.
Yep.
Any other questions before we rock on?
Great. Not seeing any. So now we do a little diversion into the philosophy of science that's behind this, because we do have to kind of understand this stuff to get what these ensembles are showing. And the spark for me was way back when I was an undergraduate. I read a book called The Virtues of Ignorance, edited by Bill Vitek and Wes Jackson. And it really focused on the limits of knowledge and how important it is to talk about what you don't know, almost more than what you do know. And I really found that an interesting slice. And the spark in the first chapter of this book, which the first essay was written by Wendell Berry, who's a pretty amazing poet and thinker, was thinking about rain falling through a forest canopy. And he posed raindrops that pass in random fashion through an imaginary plane above the forest canopy tend to leave the ecosystem as they entered it in a randomized fashion. A decent conceptualization of rain moving through a forest. He then asked, does random in this or any context describe a verifiable condition or a limit of perception, meaning random as far as we can tell? And his first answer to that was, it describes a limit of perception based on the belief that pattern is verifiable by limited information, whereas the information required to verify randomness is unlimited. So I really loved that division. And then he went further saying, what we should have said is that rainwater moves from mystery through pattern and back into mystery. And then my favorite part of all is he says, to call this mystery randomness is to take charge of it on behalf of those who do not respect pattern. To call the unknown random is to plant the flag by which to colonize and exploit the unknown. To call the unknown by its right name, mystery. And then he goes on talking about mystery. So I really like that idea that within all of these systems that we're studying, even within these models, there's some pretty deep mystery. And I think we should call it as such as we talk about it, because that really grounds, instead of going from a knowledge-based point of view, coming from an ignorance-based point of view, gets you, I think it gets you a lot farther in the discussion. And this is embedded within climate models in general. If you've read any of the IPCC reports at all, they talk about high levels of agreement, they talk about confidence, they talk about certainty and likelihood, and they've kind of codified this in what I think is a decent way, because you have to codify it to some degree. So these are three tables kind of pulled from some of their documents, looking at, you know, what happens if you have high agreement but limited evidence in a case versus low evidence and a lot of low agreement and a lot of evidence. The calibrated levels of confidence, you will see a lot of very high confidence, very low confidence, medium confidence, and then this likelihood scale from very certain to about as likely as not to exceptionally unlikely. And this is great, but what it does is it produces statements like this. There is high confidence that the ENSO, which is the El Nino Southern Oscillation, will remain the dominant mode, and precipitation variability on regional scales will likely intensify. Natural variations are large, and thus confidence in any specific projected change in ENSO remains low. Great science-like description, but if you're talking to someone who's not in this field, that's just gobbledygook words. It sounds very wishy-washy, you know, and it's very much not wishy-washy. This is very specific and purposeful, but it makes communicating this out hard. It's a good thing when a lot of scientists get together and say they have low confidence in something. You know, it means that they know what they don't know, and they know what they know, and they've made a determination. But if you're trying to defend that to the wider public, that just seems like they don't know, and so that's an issue. Right. And then quickly to kind of go all the way to the baseline, because this does matter. You know, what is science? My favorite definition is science is the study of or knowledge about the natural world. So study of is very much what a lot of scientists do. They're taking observations, measurements, running experiments, looking at the real world. And then the body of knowledge is kind of all of the textbooks that accrue and all of that accumulated knowledge in all of sciences. In my personal history, you can kind of see it here. I've stacked them based on my time moving through the climate sciences, where at the beginning, it was basic chemistry and basic calculus. As I moved into climate science, I picked up some basic books on chemistry and physics of the atmosphere. I needed more math. I got more specifics in thermodynamics. I needed even more math. And as you go, you kind of, you know, stack up into this very fine point. And that's kind of how, in any field, you become an expert. You start general, and then you kind of hone it as you go. So this would be my body of knowledge, you know, what's in these textbooks. One additional complexity that does enter here is all of that stuff that science can't do. Because science is great at certain things and it's really bad at certain things. And so one way to think about this, and I think this originated from Plato, but I don't really, this isn't my original idea, this conception, but there's kind of two giant entities out there. There's this body of facts, and science is great at learning facts and quantifying facts and getting facts, you know, set. But then there's this world of values, and they overlap in a lot of places. If we're going to make decisions or decide on action, you need both of them together. You know, why would you trust someone who's telling you to do something if they don't have any sets of values? Or why would you trust them if they have a lot of values but no facts? So this decision-making process, or, you know, what are we going to do in the future, needs both. And science itself really doesn't touch on the values. It's just the tools that science has can't tell you what you should do. It'll tell you what happens if, or what has happened, or what is, but won't give you any of that, what should we do? So we're not talking about values right now. We're zooming in on the facts, because in this sphere of facts that science is great at, there's a range of things that we were very certain about, and there's things that we're uncertain about. You know, one example of something we're very certain about is the structure and behavior and what CO2 is. This is a carbon dioxide molecule, 1 carbon, 2 oxygen. We have that really nailed down. That is very much in the certain range of science. This is an example of carbon dioxide in the mid-troposphere of July of 2009. A very specific thing, but we did have satellites running, then. So we have a pretty good idea of what carbon dioxide was in the mid-troposphere of July 2009. It's towards a certain range. There's more uncertainties because satellites have imperfections and uncertainties, and it was just one slice, one observation, so relatively certain. How about what was the CO2 concentration in the atmosphere 800,000 years ago? In this one, we've been able to use the ice core bubble proxies to get an estimate of this, but it is more uncertain than CO2 20 years ago. So this would be more towards that outer edge of the uncertainty realm. And then this, which we're going to look at a lot later today, is what's going to happen in the future. What will the Earth's climate look like be in 2100? And this is uncertain not only because of reasons based in science, but this is very much an overlap of the value piece of it. We don't know what values are going to drive decisions that'll control CO2 levels over the next 70 years. So science can't really touch on that part of the uncertainty space. It has to come from somewhere else, or has to be explored in different ways. And ensembles are one of the ways to explore that level of uncertainty. So to kind of wrap this portion up, another Wendell Berry quote here that I liked is that one of the purposes of objectivity, or kind of scientific objectivity in practice, is to avoid coming to a moral conclusion. A lot of climate scientists won't put probabilities on various climate scenarios. They're happy to run them and tell you what will happen if, but they're much more hesitant to say, oh, I think this one's true, or I think this one's more likely because of these regions. One more kind of excursion into this to understand how models see the world is, let's just imagine for the first pass that we're omniscient and we have a really good idea of the real world. We have an idea of it today. This is our kind of view of the world today. We know its past and we know its future because we're perfectly omniscient. And if I wanted to know, let's say, the temperature outside my window today, into the past and the future, I would know it all perfectly as an omniscient being. And I would be able to produce a single line representation of temperature change over time. It would be perfect because I'm omniscient. That's a great ideal, but of course, that's not how we exist in the universe. We are not omniscient. And so if we're here in the middle for today, trying to get a feel for what the temperature is outside my window right now, that's not perfect, even if I have a great thermometer. Your thermometers are imperfect. I have 3 windows here, and there's probably different temperatures in all the windows. So even that question right today, it starts a little fuzzy. It's not a strict answer. If we look into the past, things get fuzzier the farther in the past you go. In large part, this is because we don't have that many observations or proxies or ways to estimate exact temperature outside my window 100 years ago or 500 years ago or 10,000 years ago. There's specifically here different types of kind of uncertainties with looking into the past. There's availability of data. There's a lot of missing data, especially the farther back we go. There's issues with accuracy or inexactness. The various thermometers and tools to measure temperature changed over time and have gotten better today. So there's a concern about accuracy the farther back you go, or comparison of different types of thermometer measurements. And then there's things that are indeterminate, just unobservable because no one was there, or it was buried under the ocean, or it was 50 kilometers in the atmosphere. There's just no way to observe some of those, especially when you think about past records. If we look towards the future, it also gets fuzzier the farther it goes, but it gets fuzzier for very different reasons than past observations. Part of this is just the mystery of living in this universe. We don't know everything, so there's going to be some ignorance about what happens. There's unpredictability. We don't know if there'll be another Mount St. Helens eruption, or if another comet will come and give us a little bit of an ice age for a bit. We just don't know some of those things. And then the big one is this path dependency. We don't know what the future will be because we don't know what we're going to decide to do that'll change the atmosphere or the climate. So there's a human part in the uncertainty looking into the future. One way to discuss this that I really enjoyed from a book by Paul Edwards called A Vast Machine, which is a fantastic history of meteorology and the development of it, is that we'll always experience data as probabilistic, as shimmering rather than fixed, and that all knowledge about your system depends fundamentally on modeling. You can take an observation with a thermometer, but the thermometer doesn't really give you an exact temperature. It'll give you, a level on a scale that's already a model of what that system is estimating temperature. So a lot of this is shimmery. I like that idea of shimmering data. And the scientific method comes into play when talking about this too. So I'm going to give a little run through a different conceptualization of the scientific method instead of the one that I learned growing up was, hypothesis, testing, results, kind of that sequence. That almost never is how it plays out in the real world. Hugh Gao in the scientific method and practice kind of reframed it as this, what he calls the PEL model. And the PEL model has three major pieces. One are the presuppositions that you have about science. These include that the world exists, that what we see is actually there, that we can represent the world with mathematical formulas. These are crucial to the scientific method, but they're rarely talked about. They're kind of ignored as a foundational infrastructure that's at the base level. We go and we take observations of the past, proxy records of ice cores or tree ring records or measurements right now of the temperature. We take a bunch of observations. We build this body of evidence, which is the second big piece. And this includes the observations, but it also includes theoretical knowledge, how we think things work in the world, and empirical knowledge, which is like we don't really understand how this works, but we've taken a bunch of observations and we can describe, how big a stomata on a tree leaf expands during certain temperatures. We have an empirical understanding of that. The final piece of this is logic, which is simply, if A, then B, and A, therefore B. That's all there, kind of hidden below, but important to acknowledge. And if we do all this, we can develop a model. If we're talking about climate, we're going to develop a model of what we think the climate is like. And in model code, in the models we're talking about, there's parameterizations, which is all of the variables and knobs that you put in the code that you control or you estimate or you're trying to figure out. You have BC and IC are boundary conditions and initial conditions. Boundary conditions are often, one example is the emission scenarios going into the future. What are we going to force the model with as we run it into the future? That's a boundary condition. How much methane is being emitted, a boundary condition. Initial condition is you need to start the model somewhere. So you get a really good estimate at the beginning as best you can. That's the initial condition. And you run the model forward from that. And then there's the actual code and CPUs that are buried within the model as part of the model structure. And these models can be simple, one box models like we talked about earlier, or they can be very complicated three-dimensional models of varying model structures. If you do all that, which is not easy to do, and you run it and it doesn't crash, you get output, and you run it one time, you get one set of output. This is just 200 years of, for instance, temperature over the Earth, let's say. Great, you did a great job. What do you do with that? Or how do you convince people that you've done something great with your time? And this is a great cartoon from Gary Larson from 1985, which kind of feels like this when I'm talking to people who don't know the climate modeling. I've done all these things and I put them all together and I've pulled all these things. My favorite in the middle there is the square root of cat. My favorite part of any model is the square root of cat. But you do all this and then you say, I have produced the world. I have produced a representation of the world. Now the next step is convincing people or discussing your results and having them use your results to make better decisions, let's say. The trouble is you're just one person talking to them. They might have other places where they're getting information about weather or climate. There's a lot of different authorities out there. This tweet actually, I pulled initially in 2014 before the political cycles. So it's kind of funny that it's still here, but there's different sources of authority on climate information. And so you need to be convincing when you're talking about your model results. And you need to be more convincing than just saying, oh yeah, we took some measurements of ice cores back in the day and tree rings and some observations and I ran a model. That's not really convincing for most people. So you have to work harder than all of that. And the way to think about this that I really like is, let's just say this red dot is all of the climate knowledge that we've accumulated today up to this point. Great, we have a lot of knowledge. When you talk to climate scientists or go to conferences, they rarely talk about this. They talk about the much more exciting sphere of stuff that they don't know that they're figuring out that surround this body of knowledge. That's where some of the really exciting stuff is. And it's all about uncertainty and what you don't know. if over time we do grow our body of knowledge about it, we're also at the same time expanding the sphere of ignorance and uncertainty in what we don't know. So while the knowledge that we know is really important, the interesting stuff is really out in that sphere. And again, back to that book, understanding really comes from talking about and combining what you know with what you don't know. So I really like all of that. So what do we do with this? How do we build trust? One of the ways is through characterizing uncertainties. And this is where we're going to get to what the ensembles enable us to do. They let us characterize uncertainties in a way that is useful for people to use. So if we're thinking about uncertainties in this model that we ran, the example of the model that we ran, you can characterize different types of uncertainties within that model. So one of them is observational uncertainty. We talked about that. The past is shimmery, so we have uncertainties about what happened in the past. There's a lot of, within these models, dependence on initial conditions or chaos. You run it slightly differently and you get a slightly different result. So that's internal to the model. There's also internal variability in the systems we're studying and in the models. They have cycles sometimes. The sun has this solar spot cycle, that has to be incorporated. And so El Nino is a cycle that's within these systems that we have to account for that are not, it's impossible to predict them perfectly. There's going to be a bit of randomness there. And then there's the surprises, the volcanic eruptions and stuff that might be within the system that we have to also account for. And then I pull these from a Donald Rumsfeld quote back in the day where he was talking about known unknowns and unknown unknowns. It's actually a really great way of thinking about this, where there's some things that we know we don't know. We have a pretty good idea of certain things, but we are uncertain about it. So when you put these known unknowns in your model, you want to be able to tune them. You want to be able to say, I want to adjust this because I don't know exactly what this value is. I want to be able to adjust it and look at it and see how that affects the end result. So those are known unknowns. I won't talk about unknown knowns because they're rare and not really interesting. Unknown unknowns are some of the scary ones. Like if we don't know that we don't know things, how are we even supposed to incorporate that or understand that? Those are all buried within the structure, and they fit into two kind of big categories, these unknowns, these uncertainties. One of them is sometimes called epistemic uncertainties, and we'll talk about what these are in a moment. And the other group here are often called aleatory uncertainties, and they're fundamentally different for a reason I'll show here. So let's just think now about back to that rain passing through a forest canopy example. And if I looked outside my window and saw a forest canopy and I was trying to guess, let's say, how much rain would fall through that forest canopy in a given year, I could give an estimate, maybe 20 inches or 50 inches or 5 inches per year. If we all did that and kind of got together, we'd have a pretty wide range of estimates of what that would be. And if you're not familiar with these box and whisker plots, they're kind of representation of the spread of numbers. In this case, if it's a spread of rainfall per year, the line in the middle is the median guess, kind of the median value. The box represents the middle 50% of all of the guesses, and the whiskers that go out kind of show the spread of the rest of the guesses. So if we all did this right now, we get a pretty big spread of that estimate. If I spent all summer studying this particular forest and gathering all the data that exists, at the end of the summer, I would have a better estimate of what that rainfall would be per year. If I then did my master's degree, let's say, in that forest, and then went on to do a PhD and spent my whole career studying this one forest, I would reduce the uncertainty in that estimate to a pretty fine point. But the important thing is the stuff that I've reduced are all those epistemic uncertainties, the ones you can control and can do better at to kind of tune in. In the middle, there's going to be this set of aleatory uncertainties, that chaos in there, and the surprises that are largely going to be irreducible. They're always going to be there, and you're never going to be able to get rid of them. You can characterize them, but they're always going to be there. So there's this random piece or that mystery piece that's just always going to be in these projections and in these model results. And there's two kind of primary ways to look at characterizing these uncertainties. And we will do some of this in a moment with the interactive part. One of them is to create scenarios, create different scenarios of what we think might happen, or what our best guess is to what's going to happen, or what we're worried about. And this is a perturb the boundary conditions. We're changing the methane emissions over time for the next 100 years globally and seeing what happens. And this is essentially, if we have an idea of what we think is going to happen, we can build a scenario in the model and gridded emissions data set of methane for the next 100 years and say, well, here's our guess number one. There's also guess number two that starts from the same point, but diverges and differs over time. This does a lot for us and is kind of a bread and butter of a lot of the climate scenario projections, because these acronyms here are different sets of scenarios that have been developed for the last 20, 30 years. What they do is they allow us to proceed under certainty, looking at the different possible paths and trying to decide which one we prefer. That's very practical. It allows us to explore, kind of what's possible in the model. What happens if we triple the CO2 today? Does the model break? What does that look like? And that's one scenario we can toss in here. Let's just look at the model structure. It also lets us rely on expert knowledge. What is the best or most likely scenario? That is kind of an expert knowledge assessment. It's good, but humans are fallible, so there's that issue. And then it also lets us sidestep the responsibility of saying which we think is the best or worst. If we do the worst case scenario and the best case scenario and say we're hoping it's somewhere in here, you're kind of sidestepping some of that ethical responsibility of what you're doing. And then it's easy to do in models. It's easy to run different scenarios and get results and talk about those results. So that's the perturbing the boundary conditions, the scenario development. The other one is you perturb the initial conditions. So when you run a model, again, you have to have a best guess of what it starts at from which you run forward. And so let's say right now I have a guess of, my best guess of the current temperature gridded over the globe looks like this. But then you realize this guess isn't perfect. There might be a set of other ones that are all equally likely, and I tweak it. Or sometimes for some of these, you go through and you just randomly tweak it to develop a suite of initial conditions which are going to run forward. You then take these initial conditions, and in the same model that's set up the same way, you just run it forward. And if you start at time zero with this set of initial conditions, you look forward, let's say 50 years, and you get a look at what the models are doing. You go to 100 years, you get your kind of final answer of what these these 7 different initial condition sets look like in 100 years. And this actually lets us do a lot too, because in this kind of toy example, 3 of the models ended up doing one thing and 4 of them did a slightly different thing. And so now we can talk about some of the uncertainty between these scenarios or these diverging ensemble members and what that means for our model. This is in a large way the butterfly effect, how you start it with different random initial conditions. This is called ensemble forecasting, or sometimes the Monte Carlo approach to looking at it. One important thing is, other than the initial conditions, you leave everything else in the model the same. So the only thing different is that initial condition. You get a big idea of what's happening within the model when you do that. And this is a way of exploring those aleatory uncertainties, kind of those things that you can't predict. You're not going to get all of them. There's a bigger range of possibilities than we can model, but you're looking at the ones that you can simulate. So, and this is how we get, this is maybe the last 100 years of temperature of the Earth. We have one estimate of the future. This is how we get these kind of spaghetti plots of ensembles by doing something like this. And this is a lot of what we're going to look at next, and a lot of what climate model output looks like is these spaghetti plots of different scenarios. So let's skip that for now. And this is an example of these spaghetti plots. These are different greenhouse gas emissions on the top and aerosol and air pollutant emissions on the bottom from 2000 up to 2100. They have different scenarios. So you'll see here, these RCP values are different kind of model scenarios that are set up. There's ranges within them. It gets really complicated really fast, but you need these to run the models, and you need all of these for every model run. If you're gonna rely on, let's just say, RCP 4.5 scenario, you want it to be complete in all of its emissions and all of its boundary conditions. And ultimately at the end, then you'll get an idea of the radiative forcing by the end of the century under these different scenarios. So I'm not going to talk too much about the scenarios themselves. The newest ones are called shared socioeconomic pathways, or SSPs. There's a lot of literature, and there's stuff that we posted recently on the website that kind of talk about some of these pathways and what it means to have these scenarios. But a lot of work goes into these, and they're established. And then this is done so that all of the climate models, all 30 to 50 of them we talked about earlier, can run the same scenario. And so now we're comparing different models of different structures with the same scenarios, and we can look at the differences amongst those results and get another feel for the uncertainty within our understanding of the climate. So that was the whirlwind tour of philosophy, kind of the philosophy behind it. I'll do one more round of questions, and then we'll jump into the interactive part. So are there any questions about all of that?
It might not be exactly about all of that, but did a model say anything about how clouds will change in the future?
That is, I mean, certainly, if we're expecting changes in aerosol loads or aerosol size distributions in the atmosphere, that'll change the way the clouds look. A lot of cloud physics, doesn't change. The cloud physics parameters are probably the same now as they will be in 100 years, but the conditions will be different. And yeah, a lot of these models do try to incorporate that. But if you do think aerosol load, let's just say, or aerosol size distribution is going to be different in 50 years, you're going to have to input that into your model and come up with that scenario and feed it in.
Can you give me some kind of intuitive idea of how the clouds will change with climate warming?
Yeah, well, one thing, there's a lot of, and clouds it's not my expertise, so I'm not the pro on this, but some parts of it are if the cloud condensation nuclei, the little pieces that form clouds, are smaller, the clouds tend to be brighter. And so if you think that the aerosol that serve as these cloud condensation nuclei are going to get smaller, then you can come up with a scenario in which all the clouds in the globe are going to get brighter. And that would be one example of that. Another one is the color of clouds depends on a lot of things, but if we're doing a lot of work now to reduce soot emissions, and soot is the black stuff you emit into the atmosphere. And as you reduce the amount of dark stuff in the atmosphere, you're going to kind of brighten the clouds as well because there's less soot. So those are two types of potential changes that could happen to clouds. More based on my atmospheric chemistry experience than maybe cloud physics. But does that help?
Sort of. Thank you.
Yeah, and a current example is changing regulations on emissions from shipping has changed some atmospheric dynamics. Can you say a word or two about that, Ben?
Yeah, I know that shipping is very dirty emissions, and I believe was the recent reduction in sulfur in diesel fuel does a lot in changing the cloud seeding, those cloud condensation nuclei, and so we are seeing changing cloud patterns from the ships already. Yeah, that's a good one that you'd have to come up with a scenario for the future, but we can come up with probably pretty good scenarios for future ship emissions of sulfates and sulfur. Yeah.
Any other questions before moving on? Okay.
Great.
Okay.
This is the beginning of the interactive part here. So first, does anyone recognize what this is? Anyone out there recognize what this might be?
Looks like something out of Dungeons and Dragons.
That is exactly right. This is the player's handbook from the first Dungeons and Dragons book that came out by Gary Gygax. If I had a gold star to give you, I'd give you a gold star. Great, because we're going to use the dice from the Dungeons and Dragons to kind of simulate our climate modeling experience. And for those that aren't familiar, the die you're most familiar with is the six-sided die here. In the world of D&D, is called the D6, just six-sided dice. They have a whole spread of different dice of different numbers of sides. And we call them, a four-sided dice is D4, eight-sided is D8, D10, D12, and D20. These are fun. Again, D&D is fun in a lot of ways because there's an element of randomness. You roll the dice and you have to base your actions based on the results of that die, which has a random element to it. And so we're going to split up into groups, 4 different groups here. And the groups are going to be in blue, the present day group, we'll call it. The red group is going to be this 2.6. So this is one of the RCP scenarios. in which emissions are reduced pretty quickly. So a 2.6 scenario. And then there's two more groups, the 6.0 and 8.5 in green and purple. At this point, I think we can just split everyone up because there's enough here that we can just name people for different groups because we want to spread you around, because you are then going to go and roll some digital dice in these scenarios, and we're going to build our own set of ensemble runs and compare them. So what I'll do here is, let's see, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17 of us. Okay. Just remember the group I assign you, and I'll talk about what to do after I assign you. So let's do William, Manna, Kathleen, and David. You're going to be in the today group, the present day group. Colleen, Elaine, Mark, and Nancy will be the 2.6 group. Scott, James, Janice, and Justin, you're going to be the 6.0 group. And Norm, Carrie, Barbie, and Mohammed are going to be in the 8.5 group. Do we all know which group we're going to?
A couple of people are having to jump off, but
yeah. Yeah, and you don't have to participate in this. We just need enough people to run a few dice rolls for us. And I'm going to drop this link into the chat for you all here. Let's see, it was a share link. So in the chat, I'm going to give you this. And this is how we're going to do these dice runs. So go to that link and I'll demonstrate here. You can still see my screen here. Okay. So this is a handy little Google dice roller. And what it does is it has the set of D&D die here on the bottom. And what we're going to do, let's just say I wanted to roll a single 6-sided die. I would click on the 6-sided die and it gives me a roll. If I want to roll it again, I just click roll again. And I can do that multiple times. And it'll give us the total of the dice. If I want to get rid of it, I click on it and it goes away. So let's just say, for an example, I wanted to run two 20-sided die. I click on it twice, I'd have 2 dice with a total of 27. I can then re-roll them over and over and over again, as dice work. So if you're in the today group, which I assigned, the today group is 2d6, a d6 and a d6. What you're going to do is, let me get back to that. You're going to clear the dice out, get 2d6, and then you're going to roll it. And you're going to look at the total number. If you're in the 8.5 group, it's a d6 and a d20. So in that case, get one of the d6s, you add a d20, and these are going to be your rolls. So is that pretty clear?
Mm-hmm. Yep.
Great. Let me stop sharing the slides because we're going to now move to this here. And I'm going to have, we have 4 volunteers, one from each group, kind of raise your hand to be our first dice roll, just to demonstrate that it's working. So can I get 4 volunteers? All right, great. Kathleen, which group are you in?
D6 today. D6
Today, great. Can I get a volunteer for the 2.6 group? Which I believe was, let's see here, Elaine, Mark, and Nancy. Anyone there from that group? All right, well, let's move on. How about from the 6.0 group? Is anyone willing to volunteer from the 6.0 group? Scott, great. Thank you, Scott. And then how about from the 8.5 group?
I can do that.
Great, thank you, Nora. So what I'll have you all do is go and roll one simulation, we're going to call it, in those groups, and shout out your group name and the value that you got.
Okay, today group, I got a total of 4, 3 and a 1.
A 3 and a 1? Okay, so what we're going to do, I'll look on this chart here, yeah, let me zoom in a little bit so we can see a little bit more of what I'm doing here. You got a 4, so on the dice roll, we're going to find the column with the 4, and we're going to say you simulated a temperature change of 0.4 degrees is how we're going to interpret it. And we're going to add a little box right above the 0.4. So that's your run of the present day kind of scenario. How about Scott? Did you get to do a run?
Yeah, 14.
And which group are you again? You are
6.0.
you got a 14. So 14 is going to become a 1.4. Great. And the norm for the 8.5 group.
I rolled a 2 and a 6.
2 and a 6. You got a 0.8. Great. So, and let me just do for the 2.6 group. Let me just do one. 2.6 was a 6 and a D4. I got a 4. So I'm going to add to that group a 0.4. Okay. So what I'm going to do here is I'm going to zoom back out a little bit. And you just ran a climate model. We're pretending you ran a climate model and you got a result for your one simulation. And we're going to compare now these 4 different scenarios for the future. And based on this, what can we conclude about the different scenarios? Not a whole lot. We could say perhaps there's no real difference between present day and the 2.6 scenario. They give the same results. The other two are higher. The 6.0 seems a little bit higher than the 8.5, but they're both higher than the present day and 2.6.
So our conclusion might be that we don't really start to see an increase until whatever that third category is.
Yeah, right. We can certainly pull that conclusion. But also, there's not a lot of information here. Like the one climate simulation isn't really all that edifying. So what I'm going to do now is share this link, copy the link, and I'm giving you a lot of power. Anyone with this link can edit the whole document. So use your power wisely. But if you go here to the document, let me know if you can't access it. What I would like to do is spend perhaps 5 minutes running simulations over and over and over again and filling these in. And I think the best way to do it is to copy an existing block and paste it somewhere else. That's the easiest for me. So we'll give about 5 minutes to see where we are. Now for the 8.5, I'm getting a question about what those are. The 8.5 scenario is a D6 and a D20. The 6.0 is a D6 and a D12. 2.6 is a D6 and a D4. And today are the 2 D6s. So I would say go at it and start filling these in.
While some of the people are going at it, can you explain the reasoning behind using a D6 and some other numbered dice? I mean,
yeah, kind of what I'm trying to emulate here is different levels of warming, different levels of greenhouse gases with the different values that we're going to get. So the group with the 8.5 has a D6 and a D20. In essence, they're saying, I think there's going to be more CO2 in the atmosphere in that scenario because it's going to, on average, roll a higher value. There's going to be more CO2. While the 2.6 is a D6 and a D4 is actually less than the present day, which is 2 D6s. So this scenario 2.6 is one in which humans reduce their emissions and in fact draw down some CO2 in the atmosphere by the end of the century. So in a sense, I'm emulating kind of the scenarios and pretending that all of the uncertainties and chaos within the models is represented by the dice rolls, the randomness in the dice rolls.
So the 2 dice assume that climate is going to go up, the temperature is going to go up. That's the first 6 die.
Yes.
Okay, I just want to clarify.
Yep.
Okay, I have a question. I see the 20. How do I get the D6?
So you should also be able to, on the list, the images of the dice below, also click on a D6, and it should pop it up into the play area alongside the
Right.
D20.
But the D, I mean, and I see 4, 6, 8, 10, 12, 20.
Yeah, and you're doing D6 and D20?
Yes.
Yep, so you should be able to click on a 6 and click on a 20, like I did there.
Okay.
And and now you can roll. You get a 5 and a 7, which adds to a 12.
Okay. 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 Thank you.
Yep.
When I click on that link, the box where I can choose the die, it disappears almost instantaneously.
Does it?
Yeah. That's why, like, the 2.6, I don't know where the other people are for the 2.6, but so I can't put in any data or roll them.
Okay.
I'm 2.6 and I can't figure out how to even find the roller. Sorry.
Oh, no worries. I'll drop it into the chat again.
Okay. Try
Yeah.
again.
Drop into the chat. So in the chat, here is the link. You can also Google Dice Roller, and you should get to the same place. For the one that was having trouble, maybe try a different browser and see if it works there. That might get around the bug of you not being able to do that.
Okay.
All right. And while we're here, I'm going to run a bunch of scenarios for the 2.6 scenario while we're sitting here, which is 4 and 6. 2. And a 7. And a 5. All right, David, I'll add yours that you dropped in there. 2.6, 5584. 558. Oh, and Justin, I see you tossed them in the chat. Should I add those ones in? I see here.
Yeah, I just did 10 rolls. That was of D6 and D12.
Great. Did you add them to the spreadsheet or you have not?
I just put them in the chat. No.
Okay, so I'll add those to the 6.0. We've got 7, 6, 13, 14, 14.
How many did you want us to do?
Maybe another minute or two. What I'm trying to do here is get a good distribution of scenarios so we can compare. Maybe let's go until 6:10 Eastern time before we call it.
Keep rolling those dice.
Keep rolling those dice. And then Janice, did you toss yours into the spreadsheet? I see you put them in the chat.
I didn't. I just did the rolls.
Okay. And which group were you in? You were
The 6 group.
okay. The 6 group got plenty now. Okay. I'm going to run a few more for 2.6, and in 2 minutes we'll get back together. 7. One more minute and we'll reconverge. All right, we've got good distribution. So add more if you have them, but if you've got them all in there, we can step back and look and see what we've done. All right. Are we all back? Are we all done rolling our dice? Great. So this is great. This is exactly what I was hoping to see from this. You've all run now, it looks like maybe 100 climate model simulations. We're emulating a climate model run with these dice. And the different colors are the different scenarios that we ran. So different number of dice and the amount on the dice, the amount of size of the dice were different scenarios that perturbed a boundary condition example. And then using the randomness of dice rolls, we perturbed the initial conditions, let's say, and got these distributions. And so now we can kind of draw some conclusions about these different scenarios, given all of the uncertainties inherent in that model structure. For instance, the first one, we can see that the 2.6 scenario, which is one of those reduction scenarios, does seem to predict slightly less temperature change than it's like cooling compared to today, which would be the blue compared to the red. It doesn't have any extreme values. It doesn't have very high values in any of the dice rolls. We can see that the green scenario, that 6.0 scenario, does have higher predictions than both present day and 2.6. And if you squint, you can kind of see a normal distribution there, which is great. And then for the 8.5, we see something also interesting, that there's quite a wide spread. This one spans everything from 0.3 degrees change all the way up to 2.5 degree change. And so this distribution is a lot wider than the 2.6 scenario. If we were to try to draw means, what's the average for all of these? I'm going to kind of eyeball it here, but let's say, I'll bold them or underline them here. I would say that the 7.7 degrees is kind of the present day scenario, let's say. For the 2.6, let's say 0.6 is the average. And interestingly, there was only one that ran 0.6 in this case. For the 6.0, eyeballing it, maybe 1.0 would be the average. And then for the 8.5 scenario, it's weighted a little bit more down here. So let's say 1.3 would be the average. So what we've done is we've developed statistics based on these climate runs. We can look at the average comparison, which kind of fits what we would expect from these different scenarios. But we also see the uncertainty in the spreads. The uncertainty in 8.5 is very large. And even if we do, we can say the real world will be just one dice roll. It'll be one example of this. And we could say if we did do the high emission scenario, we could end up with almost no warming, or we could end up with very extreme warming. On average, we'll end up with kind of middling warming of that scenario. Any other things we can pull from these distributions that we built? Or any questions about kind of what we're looking at and what it means?
I have a question. Maybe I'm missing something, but it seems to me if you're equating the spread of the data as uncertainty, isn't that based upon your setting up of the question? In other words, you're limiting the number of data points for the present day because you only have two six-face die, whereas with the 8.5, I forgot what it was, but you have the six face and 21 face. So your uncertainty is based upon your model parameters.
It certainly is. Yeah. And so discussing the uncertainty here, you'd have to talk about one part of defending your model run is talking about what you put in, or all of the inputs that you put in. In this case, yeah, we'd say for the 8.5 scenario, we put in more warming because that's a scenario we're developing. We folded that in with that bigger dice, the D20. And that's just part of that scenario structure that it is there. But yes, you're correct about that.
And Kat had a hand up.
No, it's okay. I'm listening, thanks.
Great. Let me flip back to the slides, because let's pretend we did this, 1,000 times. We ran it a bunch of times. We would get more we would fill out these distributions. And one thing that we would expect, we don't have to talk about, you'd often get these bell curve shaped things when you run a lot of simulations that are variable like this. And it's really only when you've run hundreds or thousands of them that you've all of a sudden gained confidence, like, oh, okay, I think I understand, the spread, this 8.5 scenario has quite a large spread. The majority of it's here, but it has like a lot of these, if you look at them, they're not symmetrical bell curves. They often have long upper tails. If you look at the red one here, it kind of ramps up fast and then just spreads really, really far. There are a few that are way out there with the 8.5 scenario. And whether we want to worry about that specific scenario is kind of up to us at this point, once we've run these. Now that we've done this, I have a website that'll show us a good way of looking at this. So I'm going to drop this link into the chat, and I will walk us to it, because it's a little non-intuitive when you first see it. So I dropped that link into the chat. It's this explorer of climate scenarios put together by a wide range of organizations. And it has this nice model of the Earth with different regions. And what you do is pick a region of interest. We're in the Eastern US now, so I'm going to pick the Eastern US. And at the bottom, once you select a region, it'll pop up this regional information button. So if you click on that button, it'll bring you now to kind of these spaghetti plots. And this is a model intercomparison project, CMIP6. I believe the scenario they ran here is that high warming scenario, the 8.5 scenario. And you can see from 1850 out to 2100, each of the individual model kind of runs. All of those squiggles are individual models within this intercomparison project, what all of their results are. That thick red one in the middle is the mean of all the models. So none of the models ran that exact mean, but that's the middle of all the models. That's a good kind of, not a consensus view, but what probably our best guess would be. And so if we're looking under the scenarios given to the models, by 2100 on average, I'd say, we're looking at a 6.89 degrees Celsius increase, with that. But the spread's large. 90% of them, or the 90th percentile, is 8.5 degrees. So 90% of them are below that. And the 10th percentile is 4.97 degrees. 90% of them are above that. So we can kind of talk about the uncertainty among models here. Also, a nice one is this climate stripes. If you've probably seen these all over the place. If you click on the climate stripes tab, it shows you each model's climate stripe. And you can actually, as you walk down, see each of the names of the models in this scenario. So you can kind of backtrack and pull all of their guesses. The model that I used for my work was this NCAR CESM model. So all of my PhD work was spent doing this one model it's represented in this intercomparison project in this interesting way. And I know we have 12 minutes left, so I'm going to kind of open it up. This website's pretty excellent. You can do a wide range of variables, like frost days, for instance, in the Eastern US, it has estimates of the frost days.
Wow.
It has a lot here that you can play with and explore. You can look at past intercomparison projects, the CMIP5 versus CMIP6. You can explore those scenarios. And somewhere in here, there was a way to look at different warming scenarios. I forget, yeah. So here, if you go to climatology and changes, the scenario is that 8.5 scenario, which we talked about. I can also pick the 2.6 and see how that looks with all of the model runs. And so I'll leave you with this to play with. And for the last 10 minutes, I want to open it up to more of a discussion and question session.
And Kat's got a hand up.
Okay. Yes, go ahead.
So with you said you showed us like where all your research landed and was added to this. As there are new innovations happening, is that what I mean? How do they get integrated into all this? Like a new CMIP study, like CMIP 7 or something? And how do we know when I mean, it's clear that things are pretty hopeless, but is there any way to identify or suspect that there might be a significant change when there are, you know, scientific innovations or something? You know what I'm saying?
I think so. Yeah, so you're right with the first part that there are constantly new MIPS, ZMIPS. You know, it kind of coincides with the release of the IPCC reports. They set up these scenarios and develop them all, share them with the modelers. They run all the models, collect the data, and you get the CMIP kind of report and data set that you can look at. And as for the second one, are you asking how do we know things are getting better? Or
No, I was asking when there are significant new changes or innovations or technologies or whatever, can we suspect that those are reflected in the studies that are charted here?
yeah, those, like, you know, let's just say we came up with a great new way to do batteries, or something that dramatically decreased, let's say, methane emissions. You know, let's say we had that scenario. That would become part of the set of scenarios that would be fed to the modelers, saying, you know, we expect over the next 75 years methane emissions to vanish because of these reasons. We have these reasons. Here's the emission scenario that we want you to run in your model and see what happens to the climate on the other end. So those changes, because they're not like scientific observations of what happened or what is happening, they're guesses as to what we think is going to happen, or changes that will result from what's happening now and we expect to happen in the future. That's part of the boundary condition that you feed the models. Does that answer your question?
Yeah, thank you.
Other questions, comments, thoughts, resources?
Hi, Ben. I had a question for you. I'm an earth science teacher, and my audience is primarily 14 and 15-year-old kids. And, you know, beyond the hockey stick graph and the increase of carbon dioxide and the increase in temperature, which is, you know, used a lot, what else could you think of that may sort of whet the appetite of the young learner to just sort of show them something different about climate science that may kind of, you know, gain interest or get traction with that audience?
Yeah. I'll drop another link here too. That's a great segue into this link. This one is more of a, like, making it personal to you, let's say, you know. So, and it's Climate Explorer. If I put in Ithaca, New York, and go to a specific place, it'll provide all of these charts tuned towards your place. You know, so the climate graphs is very much what we just talked about and what a lot of people have seen. This is specific to Ithaca, New York. You know, goes back 1950 to 2100. You can look at you can look at precipitation, you can look at dry days, you can look at growing degree days, but it also gives you maps. You can look at particular maps of what changes it would look like. And this one is a nice one because you can compare historical. So this is the average between 1960 and 1990 versus what we would expect by 2090. You know, so this tool is really slick and really nice and lets you explore maybe something you're more particularly interested in.
Like where to buy your house in the future that you're going to flee to.
For instance, or the frost one, like if you look at the, you know, if you're like gardening or growing degree days, you can see the substantial difference that you'll have, you know, and you can use that. It also has historical data for different age. So if you go here and you pick a particular station, it'll show you what has been observed recently for temperature ranges and precipitation accruals. And I mean, it's a pretty excellent resource. And I do think this could be a way of engaging more because it gives students a little more control of what they're investigating. And hopefully it'll match what they're interested in.
And Dave's got a hand up.
Yes, Dave.
Yeah, I actually have two questions, if you don't mind. One, I always tell my students, I teach at a community college, so I go through a lot of this material. But one thing I tell my students is that the first question is, clouds are not really included much into models because of the inability to describe the chaotic behavior of them. Is that true? And then the second question is, Do you foresee in the future at any point where the models will become accurate enough where we can point to one model and this is going to be the answer?
Those are two big questions. Yeah.
Right.
But for your first one, yeah, the specific processes of clouds aren't resolved, we'd say, in the models, because it matters over a parking lot. The convection of a parking lot will create a cloud, and that needs really high resolution to get. But what it does happen is that the climate modelers say, well, we don't know, we can't simulate every tornado and every hurricane and every convective cloud, but we know how much heat is transported upwards and how much moisture is transported upwards over this area. And so they take all that information and create a parameterization. They say, we can't resolve it exactly, but we're going to give our best guess for what we think is happening in this grid cell on average. And that's included in the models for sure, and there's constant updates to the parameterization schemes based on new observations and new knowledge. It is constantly being updated in there. So I would say that those phenomena aren't resolved in the models, but their end results are captured in the model results, if that makes sense. And then as for the one best true model thing, if you think about the meteorology modeling, how we get all of our forecasts, they were constantly running ensembles of simulations, kind of on a rolling basis, and comparing those kind of like we did with that perturbed initial conditions to get an idea. Like, I don't know what the weather's going to be tomorrow. If I run 12 different models and 9 of them say one thing and 3 say something else, that is kind of how I base my probabilistic prediction of the future. That's in the realm of meteorology, that's very dependent on that. Climate doesn't really depend on the same sort of chaos that weather does, because there's so much in the future. But I don't think there's ever going to be a single right, like the best model, in part because there's so much that we don't know, that even if we put everything that we think we know in a model, there's still all that stuff that we don't know. And I wouldn't trust any single model to do a best guess. I would like to see 2 models where the teams developing them never really interacted and kind of came up with different best guesses and different parameterizations and different schemes, and see, if those 2 models agree, that's really good. Like, that means we probably understand what's happening. If they disagree, then we have to figure out why. And so that's part of the confidence building in a model is I never trust a single model, like, at all. And when you publish papers, you always have to compare your model to observations or other models, or justify again why you think that one model result is useful for decision makers or for action. Does that address the second question?
And that sort of raises another question I have for you, and when I talk about climate change to my students, I always show them I'm sure you're familiar with this one plot where it has the temperature data, and then it has the model predictions with this natural variability, and then model predictions with the anthropogenic inputs. And clearly the anthropogenic inputs are pretty much a lay down with what's observed. And I always tell my students that of the several thousand pages of each one of the IPCC reports, that's always the most important document, because it tells us that, one, we understand the climate enough that we can predict it, and 2, the models are telling us are working. Are those valid conclusions from that figure?
Yeah, certainly one way of trusting your model does a good job is that when you start it in 1850 and run it with, our best guess in meteorology that happened, if it looks right compared to our observations, you certainly gain confidence in that model. One trick with that is that I just lost my train of thought. I forget my second point, but yes, that would be a good conclusion from that. Bye, Janice, if you're heading out. Yeah, we are at 6:32, so if you have to leave, feel free, but I'm going to stick around for a while.
Yeah, and I'll stick in a few resources I like for thinking about, they aren't climate modeling, but thinking about where our emissions are coming from. So the EPA Power Profiler shows you the regional grids of the U.S., and you can click on that and look at. It's got an interactive map of the country where you can click anywhere and see the emissions from that particular regional grid and the different energy sources for electric power generation and the Energy Information Administration site. The second site there has another interactive map of the US where you can get state profiles and actually get an interactive map of all of the energy infrastructure in the US, where you can click on it and see production and how that's changed over time for any particular power plant and other pieces of energy infrastructure as well. And of course, PRI's climate pages have lots and lots of resources. And we're glad to stick around if there are more questions. And thank you for joining us. And I will send a link with the recording to everybody who registered.
Yeah, I appreciate you all being here. I really had a good time so far. And if there's more discussion, I'm happy to have some more discussion.
And Scott's got a question. Go
Yes.
Unmute here. Thank you. You started. Now this is a very interesting presentation. Thank you. You started with a quote by Trump, and it just made me think about how you talk to politicians conveying this kind of thing. I guess that's part of the purpose of the IPCC reports. But have you? What's your experience talking with people that make policy about what you do, and is that, what kind of impacts does that have?
Yeah, in the experience that I've had and trusting other experts who do it more than I do, the frame of your discussion matters. Like over time, we tried to move away from saying global warming, talk about climate change, because global warming became a bugbear and became a political thing instead of a scientific thing. One way, so a very famous climate scientist, Katharine Hayhoe, she's from Texas. She's an evangelical Christian. And she said, the best thing I can do to convince anyone about climate change is talk about my faith and start the conversation there to establish at least a framework of trust that, you should trust me because I'm similar to you or whatever it might be, and then build the conversation from there. A lot of ways to talk about, you don't have to talk about climate change, but you can talk about changing rainfall patterns. And, people will connect with that immediately, even if they distrust climate scientists. They've noticed changes in rain patterns or snowpack, and you can start the conversation at a more granular level and get it going. And that just in general builds more trust. It can get really complicated if politics comes in too fast, but politics, of course, is part of that value chain, or, the scenario is what's going to happen. Politics is absolutely a part of that. So it has to be part of it. But I found it more useful to talk about the smaller pieces and find the similarity and interest and then move on from there.
Thank you.
Yeah, and I put in a link for, if you're asking about policy, I have been working with the Climate and Resilience Education Task Force in New York State on climate change education policy for the state. And we are working on either a legislative approach or working with the state education department to improve climate change education in the state, which right now is really pretty terrible. And the bill we proposed advocates for teaching climate change across the curriculum, across the grade span, using the existing standards, but using climate change as examples. And that, so if you're a New Yorker and you're interested in joining us in that effort, click that link. And if you're not a New Yorker, but you're interested in what we're doing here, you can also see that on that site.
Oh, I appreciate that. I'm interested. I'm even in worse shape. I'm a Floridian, and so
Yes,
so you can imagine that my interest in this politician question. But anyway,
well, DeSantis has outlawed climate change, right? Just the other day. So.
Right.
And that mug model at the beginning, Florida's gone completely in the sea level rise scenario that climate model mug ran. So.
Yeah, I do know some Floridians who are working on it, but I know you've got a heavier lift than New York. It's heavy enough in New York.
Right. Well, thanks very much. I appreciate that.
Yeah, thank you.
Thanks all. If there aren't any other questions, we can call it a night. But if there are, we can stick around.
Thank you.
Thank you.
All right. Shall
Thanks, Jen.
Yep, my pleasure.
Yeah, thank you. This was excellent. I really appreciate your time. I was really impressed, and you know, some of the resources that you gave and some of the examples that you gave were really helpful to me, I think, for connecting to kids in the classroom. Like I said, my audience is quite younger than us tonight, but you know, one of the things that I liked that you said, and I want to actually pick, while I'm looking at my notes, pick your brain on it, is the brightness of the clouds in the future, and does that increase reflectivity does that mean more clouds and a higher albedo and more reflectivity and cooling? How does that factor in? Or I know that's not your area of expertise, but that was part of my and I was very interested in that when you said that.
Yeah, I can help, maybe in an email follow-up we can talk about that, because I can kind of look for better resources discussing the newest state of the cloud science and what they think it is, because I don't know where it is. I know for a long time it's been so complicated to model and discuss and figure out that it's a very uncertain part of the climate models was how are clouds going to act. So I don't know would be my strongest answer, but
Okay.
I'm happy to follow.
That's fair. I do love that our new standards, to your point, Don, about how New York State is not doing a great job right now. I know that, you know, with the rollout coming in the next year and 2 years, that our standards shift to NGSS, and New York State's version, the NIST list, is I think is doing something about that, and whether it's enough or not is debatable, but it is something. It's more. I think it's a fair assessment, but and that's I think really exciting, you know, for someone who's got a third of his career ahead of him yet in the classroom. You know, a change at this point is kind of cool to see.
Yes, that's the right attitude. Thank you.
I've grown up with it, Don.
Yeah. All right. Any other questions or comments? And like I said, I can I send out the slides too, Ben?
Yes, absolutely.
Yep. Okay, I will send out a email to everybody who registered with the link to the recording and a link to the slides.
I do want to ask one more question. I'm not really educated on this. I'm so grateful to have been invited. I'm not a science teacher, but I do wonder when there are like gross outliers that are just, is there any sense of conformity in the scientific community that leads everyone to always being in that what did you call them, the two pairs below and above the average or whatever? Are people reluctant to share extreme predictions because of, you know, being, you know, afraid of being called, you know, illegitimate or something?
Yeah, I mean, climate scientists are all humans, and humans do kind of gather in tribes and have camps, and there's all of that complexity is also within the climate field. So there are a few climate scientists who feel like they've been ostracized because they've been pushing, you know, they've been coming to some conclusions that doesn't align with the rest of the community, and that's certainly there. One nice thing about, you know, science often in the conferences is if you do have an outlier result, you know, the best way to talk about it is to show your results, you know, see if anyone can pick apart your results and find an error perhaps. And if not, like if you've done the science accurately and you still get an outlier conclusion, that's as legitimate as others and should be folded into, you know, the discussion. There are strong personalities in the climate world, you know, and some are on the denier side and some are on the alarmist side, but in general, I haven't felt a lot of ostracization for pushing out, but it certainly happens, and that is an issue, kind of more of a political and social issue within climate science than a scientific.
I think there's also the issue of conservative nature of science and not wanting to not wanting to go out on a limb is part of it, sort of, and just wanting to be cautious in making predictions, which I think makes them inherently more conservative, especially when it's a consensus agreement. sort of bring down and bring up the extremes, I guess, when we've got that consensus process in play.
Yeah, I think that's a real value of the model intercomparison projects, because you can see in those some outliers that are doing what seem to be strange things compared to the others, and that certainly should be part of the conversation when you assess the model comparison project, all told. Yeah.
Anything else? Let's see it.
Thank you so much, guys. I'm going to sign off. Have a great night.
Seeing you, Jeb.
Bye.
Thanks for joining us.
Thanks, everyone.
Thanks
Thank you,
all.
Don.
Yep.
Bye-bye.
Thank you, Dr. Brown-Steiner.
My pleasure.
You can call him Ben. All right. Thanks all. Have a good night.
Yep.
Do you have a question before I click off?